Hello friends, welcome back, and today we are going to solve Harvard's problem of the week number 87, named as leaving the hemisphere. The two bodies given, the first one is a particle mass of mass m1, the second one is a hemispherical surface given in the figure of mass m2. It is given that there is no friction between the horizontal ground surface and the hemisphere. On this surface there is no friction. This particle mass m1 will slide down over this hemispherical surface like this, and we are supposed to find out the equation of angle theta at which the particle mass will break the contact with the hemisphere. I have considered, to solve the problem, I have considered two frame of reference. The first one is the yellow frame of reference as shown in the figure. The yellow frame of reference is actually attached to the ground, while the second one is the green frame of reference as shown in the figure, and the green frame of reference is attached to the hemisphere. Since there is no friction between the horizontal ground and the hemisphere, I can say that a system of both the bodies combined will have no net horizontal force. If I consider both the bodies as our system, this particle mass and this hemisphere, on this system there is no net horizontal force acting on this. Hence I can say, since initially it was at rest, the center of mass is not going to move in the horizontal direction. The center of mass will remain on the y-axis only, and that is only possible that if m1 moves in this direction, m2 has to move in this direction, such that the center of mass of m1 and m2 lies on the y-axis only. Let us say particle reaches at an angle theta with respect to the hemisphere at time t equals to t0. Now in this figure you can see that with respect to fixed frame, yellow frame of reference, the hemisphere has moved backwards while the particle mass has moved in the forward direction. It is obvious that the center of mass has to remain on the y-axis of the yellow frame of reference. Now let us look at various variables in this figure. First of all, let us follow the yellow frame of reference. Let us say at time t0, when it's at angle theta, while it is breaking off from the surface of hemisphere, the velocity of particle in the yellow frame of reference is Vx in x direction and Vy in y direction, in minus y direction. And in the same frame of reference, let us say the velocity of hemisphere is V in minus x direction. So the other variables are in the green frame of reference. In the green frame of reference, I have also considered a tangential direction as well as normal direction as shown in the figure. The tangential direction and the normal direction, other than x and y direction also. The velocity of particle mass in green frame of reference will be obviously be tangential to the surface of hemisphere, and that is considered as Vr. There will be zero velocity of the hemisphere with respect to the hemisphere, so I have not considered that. So these are all the variables. Now by looking at this figure, there are too many variables. So actually we require too many equations to solve these many variables. So since we have considered two frame of reference, first equation I can write for the relative motion. Relative velocity of particle mass with respect to green frame of reference is equals to velocity of particle mass, which is Vxi minus Vyj minus velocity of hemisphere, which is minus V in I direction. So this is going to be the relative velocity equation. Now writing Vr in the vector form will be Vr cos theta in I direction. We know that Vr cos theta in I direction. I am taking the components of relative velocity minus VR sin theta in j direction, which is equals to the, I'll repeat the right hand side as the velocity of the particle mass in absolute frame, Vxi minus Vyj, minus velocity of the frame of reference, which is minus v in I direction. By comparing I and j separately, I can say that Vr cos theta is equals to Vx plus V. Let us call this equation number 1. On the other hand, by comparing j component, I can say Vr sin theta is equals to Vy. Consider it our second equation. To look into further laws of mechanics, and one I can think of is law of conservation of momentum. But conservation of momentum can only be applied if there is no force acting in any direction on the system during the interval 0 to t naught. Let us say at time somewhere at time t, between 0 and t naught, the particle is at some angle with respect to the hemisphere, and let us try to draw the free body diagram of the system of both bodies combined. One of the forces acting will be m1g, the other will be m2g, gravitational. There will be normal direction from the ground, there is no friction between any surface, and since we are in the green frame of reference, let us see whether the green frame of reference is accelerating to consider for inertia forces. Well, the green frame of reference attached to the hemisphere, and we know that this particle may accelerate in x direction. If the particle is accelerating and can accelerate in x direction, definitely hemisphere can also accelerate in x direction, but in the opposite direction. So I have to consider inertia forces on both the bodies. So let us say it is accelerating, just we don't know the direction and magnitude, just we know that it is in x direction, maybe in plus x or maybe in minus x. Let us say the acceleration of the particle of the hemisphere is a in this direction, so the forces will be m1a in this direction, and in this direction it will be m2a. Now since there are horizontal forces, I cannot conserve the momentum in x direction. Now let us consider the same system but in yellow frame of reference. What are forces will be acting? On the particle it will be m1g, on hemisphere it will be m2g, there will be normal reaction, and since this is a frame of reference attached to ground, there is no inertia force acting on the system. Hence I can say in this frame of reference there is no force acting on the system in horizontal direction. Hence I can conserve the momentum between time interval 0 to t naught on the combined system. Let us write the momentum conservation equation. Since initially everything is at rest, I can say that the initial momentum of the whole system is 0. So 0 is equals to, at time t naught, the momentum in x direction. For m1 I can say it is m1 vx minus m2 v because of hemisphere, and this is your momentum conservation equation. From this I can say that Vx is equals to m2 upon m1 times v. Consider this your third equation. Value of Vx from equation 3 to equation 1 and find out velocity v of hemisphere in yellow frame of reference in terms of Vr. So I'm going to substitute Vx in equation number 1, and that would give me Vr cos theta is equals to m2 upon m1 times v plus v. This implies v is equals to Vr cos theta divided by 1 plus m2 by m1, and I can get Vx in terms of Vr. So Vr cos theta from equation number 1 is equals to Vx plus V in terms of Vr is Vr cos theta divided by 1 plus m2 divided by m1. This implies that Vx is equals to Vr cos theta minus Vr cos theta divided by 1 plus m2 divided by m1 of energy conservation. But if I choose green frame of reference to conserve energy, I would have to consider the work done by the inertia forces, which will make things complicated. So to simplify, we use yellow frame of reference. Since there is no horizontal inertia force acting in the yellow frame of reference, I can easily conserve the energy. Let us find out what is the vertical height traveled by the particle from 0 to t naught time. Initially the particle was at a height r, and after some time the particle is at r cos theta, we know. So the change in potential energy is equals to mg r minus r cos theta. This is equals to change in kinetic energy. We know final kinetic energy is equals to half m speed of particle mass in yellow frame of reference is root over Vx square plus Vy square, and for energy I have to square the speed plus this m1 plus half m2 V square minus initial kinetic energy. Everything was at rest in yellow frame of reference, hence initial kinetic energy is 0. Substitute the values of Vx, Vy and V in terms of Vr, which we already found out in the previous equations. So the left hand side remains same, mgr 1 minus cos theta is equals to half m. So Vx is Vr cos theta minus Vr cos theta divided by 1 plus m2 divided by m1 whole square, which is Vx square, plus Vy. Vy is, see, Vr sin theta, equation number 2, half m1 Vr square sin square theta plus half m2 velocity of this hemisphere, which is in terms of Vr cos theta divided by 1 plus m2 divided by m1 and a whole square of this. This is the relationship between theta and Vr. Next we can write is a force equation from Newton's second law, but we know that to write Newton's second law equation, we must know acceleration of the body in some direction, in some frame of reference. We know with respect to hemisphere, that is in the green frame of reference, the particle is bound to, or it is constrained to move on a circular path, that is from this point to this point. Constraint, I can say that in this green frame of reference, acceleration of the particle in eta direction, acceleration in eta direction is velocity square, velocity in green frame of reference is Vr square divided by radius of curvature with a negative sign because it's opposite to the eta direction we have chosen. So acceleration in eta direction in the green frame of reference of the particle body is minus Vr square by r. This can be used in the Newton's second law equation to form one more equation, and let us write the force equation. Let us write force equation in the green frame of reference in eta direction, that is normal to the surface of hemisphere. For that we have to draw the free body diagram of the particle body at time t equals to t naught. In the green frame of reference, one of the forces m1g. Now at time t equals to t naught, the particle is going to break the contact with the hemisphere. Hence at this instant there won't be any normal reaction between the hemisphere and the particle. So there is no normal reaction between hemisphere and the particle. Secondly, since there is no normal reaction, let us try to draw the free body diagram of the hemisphere at this instant to see what is the acceleration of the hemisphere, because we are in green frame of reference. If there is any acceleration, we have to consider the inertia force also on the particle body. So in this frame of reference, the forces acting on the hemisphere is its m2g, its normal reaction from the ground. And since there is no normal reaction from the particle body, there is no net horizontal force acting on the hemisphere. Since there is no net horizontal force acting on the hemisphere, I can say that the hemisphere at this particular instant is not accelerating. It might be accelerating from 0 to t naught at somewhere at time t, but at this instant at t equals to t naught, it is not accelerating. And since it's not accelerating, I don't have to consider the inertia forces. So the only force acting on the body is gravitational force. Let us try to write the equation of force in this eta direction, which is at an angle theta from the vertical. So I can say m1g, its component eta direction is m1g minus cos theta, is equals to mass into acceleration is minus vr square divided by r in this direction. From this I can say that g cos theta is equals to vr square by r. Now you remember the equation we got from the energy conservation. That equation was also between Vr and theta. I can substitute value of G from this final equation, force equation, let us number it 4, into the energy conservation equation, and from this I can imply that Gr is equals to Vr square by cos theta, and this is to be substituted in the energy conservation equation here. Once you simplify this equation, you will get the final equation in theta as cos theta minus cos cube theta upon 1 plus m2 by m1 is equals to 2 minus 2 cos theta. And this is the final answer to the question. The second part of the question asks, what if both the masses are equal? What if m1 is equals to m2? Can we find out the angle theta? Well, let us solve that. When m1 is m2, equation will be reduced to cos theta minus cos cube theta upon 1 plus 1, that is 2, is equals to 2 minus 2 cos theta. Further simplifying this will give you 2 cos theta plus 2 cos theta, 6 cos theta minus cos cube theta minus 4 is equals to 0. This equation we will get cos theta minus 2 and cos theta plus 2 cos theta minus 2, and this is equals to 0. We know that cos theta cannot be equals to 2, so let us solve this quadratic equation. Cos square theta plus 2 cos theta minus 2 is equals to 0, and this implies that cos theta is equals to minus 2 plus minus root over 4 plus 8 divided by 2. If we take the negative sign here, again it will go out of the range of cos theta, hence I have to consider only positive sign. This implies that cos theta is equals to minus 2 plus root over 12 divided by 2, which is equals to root 3 minus 1. After solving this, you get theta equals to 42, approximately equals to 42.9 degree. This is the final answer to the question.